Welcome to Safely Syncing Real-Time Data. I'm your host, Jesse Gibson. Sean somehow managed to convince me into doing a presentation. Not sure how that happened, but let's see how it goes. Real-time data in this topic is a little bit nebulous. What exactly do I mean by that? There could be a lot of ways to interpret that. Particularly, I'm talking about a set of applications. That would be any application that manages some internal state, watches for changes over the network, and then updates itself to reflect the most recent reality. So a lot of things that would fit into this would be things like collaborative text editors, such as Google Docs or the Cloud9 IDE. You've got multiplayer games, and you've got social apps, like Instagram or Twitter or Slack or all the other ones that that are boring. Then you've got some other categories of apps that I'm conveniently ignoring, things like dashboards or video conferencing. They don't really they don't really manage some interesting things. Like dashboards, they're all one way. You almost never create events. So dashboards, they're mostly one-way sync. So that makes them inconveniently boring for this presentation, and I won't be discussing them. The next part of this, if you remember my title, it's safely. The word safely implies there's some danger. Why do we think that real-time sync is dangerous? Well, to explain that, I'm going to take a little bit of a detour and talk about databases. This is an architectural diagram of a really large app. If you look on the left, you'll see databases. On the right, there's also databases. Mostly down the center, it's just more databases. The entire thing is databases everywhere. And why you might do that is because your app has grown to a size where one server running one database can no longer handle all that load. It would just get pummeled and it would die. So instead, what you do is you take a complete copy of that database, a replica, and then you load that onto another server and you spin that up. And so now each one of those individually can handle its own little fraction of the load. And it becomes a lot more easier to manage and a lot easier to scale. But there is a little bit of a trick there because they all have to talk to each other, probably not in this way. But as soon as you write to one of those databases, now the rest of those snapshots, those replicas, are no longer valid. They've been changed. And so you don't want to have out of sync information, so you have to synchronize every single one of them. You have to listen for those updates on the network and update itself. That's where things get a little bit tricky, because the network can be a little bit unreliable. You can get updates out of order. You can get duplicates. You can get concurrent writes, two people trying to write to the same thing at the same time, causing conflicts, and conflicts give rise to divergence. That's when two databases not only disagree on what the state is, but often are going in very different directions. And once you have a divergence, it's very difficult to get them back into sync, to get them to agree on that data. And when you have, if you have a database that you ask it a question and it gives you different results depending on who you ask, that's not very useful. So this is a bad thing. Why do we care, though? This is a JavaScript meetup. Why are we talking about databases? Because I think this is actually the same problem. When we're talking about a real-time web application, every browser maintains its own database, its own place for data, whether that's on disk or just in memory. It's a tiny little replica of what you have on the server. And you're listening to messages over the network, much like that cluster, listening for writes and updating itself. And even then, this is a worse network. We're not going to have as good of a network or as reliable of a network as you would in some Amazon Web Services cluster. So it's actually a little bit worse. And we're also susceptible to exactly the same problems. Updates arrive out of order. You have duplicates. You have concurrent writes, people trying to change the same thing at the same time. You have conflicts. And yes, you have divergence. Because when was the last time you heard someone say, just refresh the browser page? That's a divergence. That's somehow we've fallen out of sync with our server, and the only way to recover is to completely pull that new state down, wipe it out. So a little bit of a clickbaity conclusion. Real-time data sync is hard because it's a distributed systems problem. That's a pretty scary conclusion, right? We don't want to, like at that point, you might be going to your product manager and saying, guys, we need to scrap that feature. It's just, we don't want to go down that road. But someone's had to have solved this, right? I mean, we look at databases. Databases work. How do they do it? Most of the time that comes down to write locking or some variant of this. It would be making sure that, well, A, you've only got one server that actually can write. The rest of the databases are just copies, and they can only serve out reads. And so everyone pulls from one central database and propagates out. The other way is to have some kind of consensus algorithm like Paxos or Raft, or probably something similar that would make sure that only one person is writing to the same thing at a time. That avoids conflicts, and it makes the rest of the convergence a lot easier to manage. But try doing that in a browser. Try making sure that only one browser is writing to the same thing at any time. That's a very difficult problem. I'm not going to say it's impossible, but I've never seen anyone actually try it. So that's what servers are actually for, right? When we send some request to the server and say, hey, I want to change this data, I want to update this, they're the ones blocking that write. They send that off to the database, and the database is that layer that makes sure that only one request is getting processed at a time for that particular resource. So it's our write lock. But that doesn't always make sense for a couple of applications. For some things, that's just not feasible. The server becomes our bottleneck. Things like that would be multiplayer games or collaborative text editing. Like for a first-person shooter or something similar, you can't stop the world. You can't say, hey, you've got a merge conflict. Would you resolve this for a minute? No, that just doesn't work. And plus, waiting a full second for a server to say, yes, you've actually killed that person, that is, good game, plus 100 points. That doesn't play well. Same thing for collaborative text editing. Imagine waiting for a round-trip request every time you type a character. And that's not just you waiting, that's everyone else waiting. And that gives them more time to make their own changes and overwrite yours, and now you've got conflicts, you're right back where you started. So how do we solve that? Like, we can't follow in the path of these write locks, and so what do we do? Well, this is an interesting history. People have actually tried this before. And so kind of going back in time, 2009, Google released a product called Google Wave. And this may bring nostalgia for some people. It might bring horror to other people. But at that time, it was one of the most ambitious real-time apps ever attempted. And under the hood, all their collaboration features, like collaborative text editing, almost kind of like Google Docs or just sharing and all that, that was all implemented on something called Operational Transform, or OT. And it was terrible. It was terrible to work with. It kind of evolved out of people saying, how do we think this should work? Trying it, shipping it, and getting bugs and fixing those bugs, rinse, repeat until you don't get any more bugs. So there's a little bit of trial by fire there. It wasn't very solid in some ways. It was hard to get right. It was hard to prove that you did it right. And if you ever needed to maintain that, you lost all guarantees. Process begins again. And especially once you tried scaling that, because it was all written for with the idea of mind of like one server. That's, you want to get something working. Trying to get that onto a second server made the problem so much more difficult, because now it's a distributed systems problem. Bring in the research papers, enjoy your life of pain. So clearly this is not a solution. You're not thinking, gee, I can't wait to ship this, right? I hope not. Thankfully, in 2011, there was a group of researchers that came along and looked at our field and discussed and said, what have you done? This was once beautiful. And so what they did was they sat back and formalized possibly the most ambitious CAP theorem trade-off the world had ever seen, something called conflict-free replicated data types. And that offered a pretty attractive guarantee, something called strong eventual consistency. And to my knowledge, nothing else has ever done this. This is one of the most interesting trade-offs I've seen. And basically, it says that after all of your updates have propagated through the system, your copies, your replicas, your app state is guaranteed to be identical across all of your systems. That's a pretty powerful guarantee. That means no coordination, no consensus, no rollbacks or anything like that. You just make an optimistic update and you send it out. You're not waiting for a server to say, hey, yeah, that change looks good. That database says you're not concurrently editing something. You just push out the write. This guarantee is your validation. This guarantee is the thing that says you're good, that write succeeded. So you just push that out and you're done. That is pretty fantastic for a number of reasons, but some of the advantages that gives kind of speak for themselves. First off, now you've got a stream of updates. This is very easy to share. This is very easy to stream over a WebSocket or a WebRTC data channel. Also, it's offline friendly because you're not waiting on a server to give you that validation to prove that this worked. And then you can edit your app. Your app is still functional completely offline. And when you get back online, you just push those updates out. You resync with your cluster. Everything's guaranteed to reconverge. That's pretty cool. It's also fast because, once again, you're not waiting for a server, and it can be done completely peer-to-peer. You don't need to have any central authority in the mix, and that makes it very cool for my own selfish reasons, namely not wanting to pay for server space. So people started to notice this, and it began taking off in a couple of really interesting spaces. Things like distributed systems, database designs, file sharing, and text-based collaboration, the field it was originally designed for. If you've ever used Atom's teletype feature, under the hood, that's actually just using CRDTs. There was a downside, though. I lied. It's perfect, and they actually solve everything. So where does this fit into your system? Oh, this is it's a little bit nebulous. What do we need? Where do we need to put it? Well, the general idea, the general place, or the structure of this idea is that it's a set of rules for collaborating on a shared mutable state. It tells you what you can't do, what's dangerous, and thus is off limits. How you kind of use this in your code is it'll look something like this. You'll have a merge function that takes your entire app state and someone else's entire app state, squishes them together, and that's your next state. And squishes is a technical term. So you continue on with our state, and you repeat that process for however many people you want to sync with. That is called the state-based CRDT, or convergent replicated data type. It is one of two main ways of approaching this. Also, I should note that you don't need to have the full state. It can just be a patch. But for the purposes of a presentation, it's much easier to model to explain that. Essentially, all of those constraints are on your merge function. That's where the CRDT magic actually happens. Those properties are, your merge function has to be commutative, it has to be associative, and it has to be idempotent. I'll get into those in a second. But once you've got all of those, once your merge function is completely aligned with those three goals, then you've got a state-based CRDT. And you can relax along with the flexibility and peace of mind that comes with that. If you fail to implement any of those properties, or if anything, if you ever mess up one of those edge cases, then your systems will surely descend into chaos. You no longer have a CRDT, and good luck with your life of pain. So we don't do that. Instead, we do it right. How do we actually go about implementing those properties? What does that look like in practice? Well, first off, that first property, commutativity, this one's the most difficult to actually do because we're so used to depending on this. Because updates can arrive out of order in the network, the easiest way of preventing that kind of issue is just by not allowing you to depend on order. So these two things should always produce the same thing. If they don't, you don't have a commutative function, you don't have a CRDT, you've lost all the guarantees. So you can't depend on order. Next thing is associativity. This one's a little bit more hand-wavy, more difficult to wrap your head around, but essentially if you merge things in different orders, you have different groupings of things and that produces a different state, then you no longer have a CRDT, everything explodes, the world is pain. The third thing is idempotence. Basically means you automatically deduplicate things. Doing the same operation more than once has no effect. You just only treat the first one specially. That's a lot of words. That's too much talking. Let's actually look at some code. Are you ready for this? There it is. Thank you for coming to my TED Talk. Okay, more specifically, the set union function. Speaking of which, how many people are familiar with ES6 set, JavaScript set function or data structure? All right, perfect. I'm gonna jump over that really quick then. It is essentially a list that is unordered, and all items are automatically deduplicated. So it's a bit like a mix between an object and an array, where a key can only be added one time. If you try and add that key again, you're overwriting some value. But it's in the sense of a list where there's no key value correlation. It's just the value. So you add a value to the set. You check, is this value in the set? Yes, it is. And you can pull it out. So that's the general gist of the set. This thing that I'm doing here in the code is saying take all the items from this list and all the items from this list and stuff them together. And the product is just the result of those two things. So why is this a CRDT? I don't want you to just take my word for it. How do we verify this is actually true? Well, first off, it implements all the properties. And if it implements all the properties, no matter what how they term that, how they describe it, it is a CRDT. So first off, it's commutative. Adding things in different ways doesn't change the result. You'll always get the same value out of that. It's associative because if you add different groups of things, if you try and if you merge them in different orders, it doesn't have an effect. It's still the same thing. And also, it's idempotent. Things are deduplicated. That's kind of the whole point. So yeah, it's a CRDT. There is one catch of that. You can't delete things. There's no way to model that in union. Like if you're taking two things and squishing them together, merging them all, there's no way to delete that. How do you delete by adding? You can't. It doesn't make sense. But past that, there's a deeper reason for this. It's first, deletes break commutativity. Adding something and then removing it is very different from removing something and then adding it. You get a different state. It's not commutative, therefore you don't have a CRDT. So we don't do that. This idea is called the grow-only set, and it's the base for pretty much every other CRDT I'm going to describe. Before I move on, are there any questions?
So if I'm tasked with writing a unit test, okay, we hate those, right? For this, and so I've got all these clients updating and doing stuff, and I just say stop. Okay, I know that nobody's updating anybody anywhere. How do I ask the question? Are you all in sync? How do I ask? So I know there's no updates going on anywhere or anything, and so it could be like a situation where it's not real time, it's just static database, and just moving data from one database to another. How do I query that everyone's in sync and get an answer back?
That would probably have to happen at development time, waiting until, pausing everything, waiting until all the updates propagate through the system. Once the network is at rest, then doing a literal comparison against the database. Maybe that's just hashing or keeping track of a Merkle tree or something like that.
And that was it. Like after everything stopped, and I know it stopped because I'm controlling the updates. I'm writing a test, and I'm doing updates over here. So how do I just ask that? How do I know?
Yeah, you'd have to write that logic yourself, unfortunately, and that would. I don't know how you'd actually do that in a production environment. It would have to be in a test environment. But yeah, essentially just waiting for everything to end and then literally just comparing those databases. So does that answer your question?
Right, but in developing this product, they have to do that proof, right? They have to do that proof. They have to go through this same exercise, not just for me, as a developer, and developing that, they have to go through that proof to prove that all of this stuff works.
Yes.
And so they have to stop everything and say, is everybody in sync? Okay, we're good to go. Let's ship it. Mm-hmm. So I'm just wondering about that. How do you query that? How do you ask that question? And how do you get an answer very quickly? And then, it's a yes or no. And if it's yes, continue. If it's no, what do you do?
Yeah. If it's no, then that means your system is broken. Naturally, and so at that point, you've got to take a much deeper look at this function, kind of investigate it, prod it, and there are some tools that help with this. Things called property-based testing. You can essentially say this function is commutative, throw data at it, and it'll tell you no, it's not. It's this thing. If you plug this in and that in, then you get a wrong result. Check it, fix it, and so that'll help debug those sorts of things. But I will go on a little bit later and kind of explain that we probably won't have to build these things ourselves.
Yeah, and I'm not saying that we should test it or develop it. I'm saying if we're going to use this or use this this feature, this technology, that has to be done, and I shouldn't have to think about those things. I shouldn't have to write those tests and ask those questions. But how do they do it? How is that done? to prove to me that works. And I believe it, I buy into it, but it's just the proof and the validation.
Ah, yes. It has been mathematically validated by people much smarter than me. Yeah, that's why I trust it.
But I want to start down that path until I get lost, until I say, okay, you got it, okay. So that's just what I'm going. So.
Yeah, okay, cool. And then, did you have a question?
No, I was kind of, thinking of that problem as he posed it was, it's more, and you kind of answered it with mathematically it works out. So if you have those three properties, if you can test those three properties on your function, and if you have those three, you have a CRTP, correct?
Exactly.
Okay.
Yeah.
So we're doing updates, but rather than a delete add, we're just doing add. And just reflecting the most current or whatever snapshot you have.
It's all just a merge. There are no deletes. You're just adding everything from every replica. So yeah, I'll get into a couple more concrete examples here after that. I just wanted to make sure that kind of that grow only set was, or that the properties of the set itself were at least more explained. Cool. So how do we do something useful with that? The most simple example of that, the most commonly reached for in documentation, is something called the grow counter. And as you might imagine or infer, it counts things. All the members of that set, it kind of works like this. You've got that grow only set where everything you plug into that set is a number. And in order to figure out what that value is, you sum everything together. You just add it up. So it'd look a little bit like this. And so you've got -2, 3, and 5. You sum all those things together, it comes to 6. You're not actually keeping the number 6, you're keeping the set. And you're merging the set. And when you want to change this number, you'd add another number, and that changes the derived value. And so you can just send that update to your other replicas, say, merge this into your set, and they will derive the same value. That's the guarantee. There's a little bit of a difficulty here, as you can see. Like, if we were to add the same number, say we want to get to 9, we can't just add 3, it gets deduplicated. So how do we work around that? That's where you'd add IDs, because I lied a little bit. That's not actually the accepted implementation. Rather, this is, where you have an association of ID to number. I just chose strings because it happens to work out well in JavaScript. In many other languages, you'd probably use a tuple. JavaScript doesn't have tuples, and so strings it is. In this case, A, B, and C are the IDs. They're randomly chosen. They're up to us. You just plug anything you want in there so long as it's low guarantee of collision. Then on the right-hand side, you've got your number, and so you parse that out as an integer. You can derive all that. So 2 and 2 and 5 is 9, if I can do math. That kind of raises a little bit of something that's been implicit, but I haven't said explicitly, is that your derivation function, the way you derive that count, is different from your merge function. Because your app doesn't care about the set. Your app doesn't care about these strings. All it cares about is the number 9. This set is a way to get there. And so more commonly, you're going to have something split out a bit more like that. For every update, you're going to merge that update, and then you're going to rederive that state. And oftentimes that can be done incrementally, but there's no difference aside from performance of just deriving that completely. In this case, for this function, you've got your set union, which is your actual merge function, and your derive function is the thing that actually iterates over the set, splits it out, parses that, and then adds it all up to 9. So that's kind of the division there, and that's usually how you'd see it done. Still, that's just a counter. We can't really do much with that. We're not going to build the next Facebook on a simple count, so let's dive a little bit deeper, build a little bit more. Something else to mention is you don't need to choose just one CRDT. You're not going to build one CRDT that implements the entire functionality of your app. That's not feasible. That sounds terrifying. Instead, you'd use these smaller pieces, like a counter itself, and plug those together into using kind of like, as though they were primitives, building something more complex out of that. The next one is called the two-phase set, or 2P set. It allows you to actually delete things, which if you told your product manager, sorry, we can't delete things, he might look at you and say, are you a real developer? And at that point, you have to say, I don't know. So instead, you have two sets, one for adding things and one for deleting things. When you add something, you put it in the add set. When you delete something, you put it in the delete set. Kind of self-explanatory, but the interesting part about this is how you derive it. And that's a little bit of a pattern you'll see as we go on. Most of the logic we write will go in the derive step. So what we do is when we're iterating over this first addition set, that's where we get all the actual information, we check, is this in the deletion set? If it is, ignore it, pretend it doesn't exist. And so in order to delete something like the value 4 from our produced value of 1, wait a minute, no, that's already deleted, yeah. So in the set 135, if we wanted to delete the number 3, we'd add that to the deletion set, and then whoever goes to derive that will now see 3 as missing. And that's something called tombstoning, and it's pretty common in distributed systems. So instead of actually doing the act of deleting something, which doesn't commute, you add the instruction to delete something. And everyone executes that, and it's something that you can actually send. It's something you can look at. It's something you can touch, and it sticks around.
Real quick, if you can't remove it from addition, so let's say we're talking thumbs up, right? So I thumbs up something, that's the addition. And then I say, wait, I didn't mean to thumbs up it. So I take it away, that's my deletion. And then I realize, no, actually, I didn't mean to give it a thumbs up. Can I give it a thumbs up like that?
You cannot. That is a caveat of the two-phase set. I actually have a slide for it. I'm psychic. You can't add something, delete it, and then add it again. And likewise, you can't delete it again. That can only be done once. That's a constraint of this implementation. But there are other ways to do this, other more clever ways. And this one's called the observe remove set. It allows you to do that more than once, which is pretty useful. Instead of having just the value literally in your addition and deletion set, you associate an ID, much like you did with the G counter. And instead of deleting that value by putting the value inside the set, you have to declare every single ID that thing has ever gone by for it to be considered deleted. And that basically works around this problem, because if you want to add a new item, you just add a new item and it pops up in that addition set, you rederive it. If it's not in that deletion set, it exists. And if you want to delete it, you just add that ID there. So you can continue that process infinitely, and finally you can delete and add things more than once. Oh yeah, I had a slide for that and I missed it. The next one here, we're kind of getting into more interesting ones. This is called the last right wins element set. It tracks a value over time, and if this sounds familiar, that is basically the definition of a variable. We're building a CRDT that implements a variable. And that kind of works by, well, the same pattern we've been seeing. You've got some incrementing value. When you want to set this value, you add a new item to the addition set. And what you do when you derive this is you look for the highest number, and that highest number is your current value. And so in this case, it's third value. If you want to delete that thing, then you find the highest number, add 1, and put that in the deletion set. And your derivation function, when it comes along, should say, this thing has been deleted. It is considered undefined. It does not exist. And then if you want to add it again, naturally, you can just add a new value of 5, and it's back again. This is where the composition gets interesting, because you can use this last right wins element set as not just a variable, but as a value inside something more complex like a dictionary or a list or a linked list. And so you can start to build out more interesting patterns from this. There's something I should probably mention on conflicts here, because this could slip by. What happens if two people add to the same, add different values with the same count? What should we do in this case? Does anyone have any ideas? I'm curious. Yes! That is a good answer. I like that. The trick is, it doesn't really matter. What matters, what we're going for, is convergence. Whatever we do here, everyone should agree that that's the path forward. That's the thing we accept as the real value. So it doesn't matter whether we choose iPhone or Android. Our derivation function should just pick one and make sure everyone picks that same one. One of the simplest ways to do this in practice is just a string comparison. I'm not certain that would actually work cross-platform, because JavaScript does weird strings, UTF-16, yay. But For everything in the same JavaScript environment, yes, that will handle it deterministically. So which is the larger of these two values, just pick that, and now everyone has chosen the same value. Similar thing with this case. If we've added a value and deleted that same value, what should we derive to? The answer is, it's up to you. Just pick one and make it consistent. So most implementations of the last right wins element set will give you a configuration that says favor deletions or favor additions. And so long as you set that same thing everywhere, all of your replicas should converge. There's a little bit of an advantage there, and I've completely spaced it. So moving on. Garbage collection. Because you now have this ordering, which is much different from the OR set. Let me go back a couple of slides here. Yeah. Although I've numbered those things there, really these would be UUIDs, and you wouldn't know which one comes after the other one. So they're all just, for all you know, they're basically, they happen at the same time. But with that last right wins element set, it's kind of spec'd out that you have this monotonically increasing number. You keep on counting upwards. And so you have that extra information of which one is the most recent. And that gives you a little bit of an advantage, because you can say, 3, I already have a value 4. 3 will never be useful to me ever again. And you can safely discard it. I'm not saying send out a message that says delete that everywhere. Just ignore it on your own replica. And it might pop up somewhere down the line when someone else sends you an update. Just kind of take that, say thank you, and then throw it in the trash. But that is a pretty unique behavior of the last right wins element set, because many of these things, as the name implies, grow only set, they keep growing and they keep growing. There's a lot of metadata, and CRDTs are somewhat well known for accumulating and never letting go. So if you have a lot of metadata, this might be a neat little trick. Now, there's a more clever way of doing this. This is one of my favorites. It does the exact same thing, but instead does it smarter. So instead of having 2 sets, you only have 1 set. And the theory goes here is if the number is even, it's considered deleted. If it's odd, it's considered added or set, reinitialized. So when you go to derive this thing, it's the same thing. You're looking for the highest value. Ignore the rest. If that highest value is an even number, it's considered undefined. That kind of circles back to there are many different ways to do the same thing. You can implement the same, observe remove set, last right wins element set, and like the max change set. Those are all basically doing the same thing, but there are many different ways to do that, and they all have their different trade-offs. So I covered many a thing. Are there any questions at this point?
How does this work with multiplayer games?
Oh, I should have included a literal example of that.
Is this what they're using nowadays? Is this why there's so many hackers out there?
I hope so. That would actually make me happy under the hood. Yeah, so any other questions about that?
So in the deriving step, and then maybe you're getting to it, are these ever-growing sets where your derive step is like iterating, right, like that factor as they grow?
Yeah.
Is that like, is there a solution for that you're getting to?
I am not.
Okay.
Yeah. Thankfully, most of the time when you're taking some update over the network, instead of having to rederive that thing, say your set has 1,000 items, the next time you receive an update, it won't be iterating over 1,001. Most of these things are very easy to continually update in real time. So you can have one state and say that most recent thing is version 3 value, and you get a new one, version 4 value. You can incrementally replace that. And so you don't have to reiterate over the entire set to know that this is how to merge these 2 items. So a little bit of... Yeah. Yeah. Okay. So little bit of notes on JSON. Like sets, there's no counterpart of a set in JSON. There's only objects, arrays, numbers, booleans, and strings. So how do we actually get this to other people. That's kind of important, right? It kind of, well, let's look at that for a second. How would we get that into JSON? Anyone have any ideas? Beautiful. Yes. You got it right, yeah. So object is probably the closest thing to a set in JSON, because all of the keys aren't deduplicated, right? If you try and add the same key more than once, it just doesn't have any effect. Now, that is a little bit tricky with the value. If you try and overwrite something with a different value, then naturally that updates the value. So we always just hard code that thing to true. Keep all of the meaningful stuff in the first parameter. And so that's kind of our JSON workaround. And when you want to go to rehydrate that, it's also pretty easy. You just grab the list of keys and plug that into a set. Now, if you did want to get a little adventurous, I didn't actually make a slide for this. You could use 1, 2, and 3 as the keys, and then the values on the right-hand side. That does mean that where your set would normally handle the conflicts, not really the conflict, yeah, the conflicts, where you have 3 with one value and 3 with another value, that is implicitly wiping out one other value. It's doing a delete and then a re-add. And as we know, that doesn't commute, doesn't work. We can't do that. That's a little bit of a subtle difference, because now your conflict handling moved from your derivation function, which is safe. If you make an error, a logic error in your derivation function, you can just fix that and push out a new version. If you do that in your merge function, all of the stuff that you did with that merge function is potentially bad, and I'm not sure how you could merge that. Hopefully everything was just in memory. As soon as you've moved that problem from your derivation function, which is the conflict from many a slide ago, let's see where that was. Did I go too far? I did, yeah. So when you've moved that conflict handling from your derivation function to your merge function, it has to be a lot more robust. You can't make a mistake. It has to be a lot more rigorous. So be careful on that. Use the exact same conflict handling logic. Make sure it's solid. So long as you do that conflict handling, you will be safe. Let's see. Oh no, too many, too far. Yeah, okay, here we go. There are many other topics here that I didn't really cover. There's an entirely different way of doing this called operation-based CRDTs, which instead of merging states together, you have your state in an operation, then you rebroadcast that operation instead of your next state, your patch. And that is a little bit simpler, but also has different trade-offs and issues with it, and also kind of expanded scope and would probably get things confused. Another thing was modeling collections. You could take a set and associate a last write element set with a last write wins element set with some key, and as you're deriving things, say, is this key new? Then yes, create a new object for that. And then as you're kind of going through, add that key to the object and derive the value of the last write element set. Put that as the value, and so you can kind of derive out objects, and you can derive out arrays. Whatever you put into that set is completely up to you, and if you think you can use that information to derive something more meaningful, by all means, go for it. And then minimizing metadata, there are a couple different tricks on this. Some ways that you can say, all right, after so many updates, kind of squish all of this stuff together into a new value, and then continue on from there. And if you get a little bit clever with it, you can essentially squish information and kind of compact it and get rid of all of that past history. But I don't really have time to go into that. I think I'm already past my time, 8:25. So that's pretty much everything I can talk about at this point. As I mentioned, I attend these meetups pretty often, so if you ever have questions, I'll probably be here. A little bit on ulterior motives. This episode was brought to you by Ulterior Motives. I love CRDTs. These things get me stoked. I want to use them everywhere, and I want to use them at work, but for that to happen, people need to know about them. They need to trust them, and there have to be tools for this. And for tools to exist, you need to have a lot of hype. So this is where you come in. Join me in spreading the CRDT propaganda, fill their minds with this, and we'll build the hype, and together we can change the real-time landscape. Thank you.